Hello, in today's video we're going to break down Newton's law of gravitation and show you how even something as simple as your weight is a part of a much bigger cosmic story. In 1687, Isaac Newton proposed one of the most important laws in physics, the law of universal gravitation. This law says that every particle of the matter in the universe attracts every other particle with a force. That force depends on two things, the masses that are involved and how far apart they are. You can see that we have our equation right here where the mass of mass 1 times mass 2 is divided by the distance times our gravitational constant. That's their attraction. We know that r is the distance in between those two, and g is going to be a constant, which is listed down here. This formula tells us something wild. The further apart these two objects are, we can tell that their gravitational pull or force becomes weaker. That's why stars trillion of kilometers apart barely feel each other's gravitational pull. So we're gonna go to our next page, and this is like the idea how stars are very far. Their gravitational pull is almost zero. Now let's apply this idea to you jumping into a pool. When you jump into the pool, the Earth pulls you down. But crazy enough, you also pull the Earth up. Just that your mass is so tiny in comparisons that you don't even notice. For example, you would have to be falling for like 1 year straight just to pull the Earth up around 6 nanometers. Now let's apply what we learned to a problem here. Now it asks us, what is the gravitational force in between these two planets or particles we're going to use in this situation? We're given the mass of the two, the gravitational constant, and the distance between the two. So now we should write down our equation, how we're going to solve this. So we know the gravitational force is equal to the gravitational constant times 10 to the negative 11th power newtons meters squared over second squared, and then it's going to be times the mass of the particle 1, which is going to be 0.500 kilograms, and then we're going to multiply it by the mass of the second particle, which is 0.0100 kilograms. And then we're going to divide this all by the distance squared between them two, which is going to be 0.05 meters. We can see that our units should cancel out. Kilograms times kilograms is kilograms squared, which is going to eliminate the kilogram squared in the denominator, and then the meter squared divided by the meters down here should just leave us with newtons, which will give us our final solution. Now just plug this in your calculator and you should get 1.33 times 10 to the negative 11th newtons. This force is very tiny. Gravity is actually one of the weakest forces in nature, surprisingly enough. And now that we know the gravitational force between the two particles, which is applied equally, now let's find the acceleration of the two particles from their gravitational force. Let's start by erasing what I written here previously so I can have some space to solve for it. So we know that to find the acceleration, we're going to use Newton's second law. So what it is the sum of all forces equals to mass times acceleration. And we know the mass, we know the force, so these two particles are going to accelerate differently even though the sum of the forces is the same for both the particles. And that's just because of the inertia of the larger object. So we're going to move our force up here. So acceleration of the first object m1 is equal to, we're going to have our force, which is 1.13 times 10 to the negative 11th newtons, over our mass, which is going to be 0.500 kilograms. This should give us a pretty small number, because these are very small particles, keep in mind. And if you put in the numbers, the first object should be accelerating at 1.334 times 10 to the negative 8th power. So you can see like how weak this gravitational force is. Now let's find the acceleration of the second particle. How fast is this one accelerating? So we're going to use 1.33 times 10 to the negative 11th power, again, divided by the mass. And this is going to be 0.0100 kilograms. And once you put in your calculations, you should get 2.66 times 10 to the negative 10th power. And as you can see, the object that has the larger mass should be accelerating a lot slower. So I think I switched these values around. But anyways, the larger object accelerates slower compared to the smaller object. And that should be it. Now, thank you for watching my video today, and if you enjoyed watching this video, please like and subscribe to motivate me to make more content just like this.